experience, intellect and emotion, and knowledge and wisdom through the means of dialogue between different disciplines. Through this multidisciplinary program Bridges aims to develop ethical action plans for creativity for conflict prevention, as well as
Bangkok hosts, some of our board members, and it's fantastic to be here together as a community. Of course, the most important audience this morning is our students, and we are very, very privileged to have someone, Dr. Schmidt, standing as a Nobel for being a partner with NIST for close to a decade now for making this happen. So we're very, very fortunate, and I also really love the overarching theme, and that's bringing peace to the world. So that really ties in very nicely with not only our school and our community's mandate, but what we're hoping that you, as students, can help to do throughout your lives. So, without further ado, I'm going to pass it back to the wall, I think, and welcome our special guest here once again. Thank you.
Professor Schmidt is a 2011 Nobel Laureate for Physics. Currently working at the Australian National University's Research School for Astronomy and Astrophysics, Professor Schmidt received his own undergraduate degrees in physics and astronomy in the University of Arizona, and has a PhD from Harvard University. Professor Schmidt and his team traced a special type of supernova called Type 1a, which occurs in a binary star system back in time to track the universe's expansion. His results not only show that the universe is expanding, but it's also accelerating. This earned him numerous awards from all around the world. Other than researching and teaching, Professor Schmidt also does keynote speeches and runs a vineyard and winery in Australia called My Penrod. So here he is as a keynote speaker. Could everyone please stand up and put your hands together for Nobel Laureate Professor Brian P. Schmidt.
Anyway, it's a great pleasure to be here, and it's great. It's my first time actually to be able to come to Bangkok and see something other than the airport. I've been to the airport about 50 times, but I've never had a chance to see Bangkok. So today's discussion is going to be a discussion. I'm not going to go through and give my keynote talk. This is about you guys asking questions, but I want to set up the questions before we go on. And so, I think the first thing to realize is that I grew up in the U.S. state of Montana and Alaska. And I went to a school similar to this one, a very good school, but it was remote. And one of the beautiful things about the world we live in today is how connected it is. And there's no place and no thing more connected than science. So I, from being just another student in another classroom in a remote part of the world, was able to go through and make a discovery that the universe was accelerating. What does that mean? It means when we look back in time, we see that the universe is expanding. That is something that Edwin Hubble realized in 1929. And the whole idea that things are moving apart is fundamental to the universe we live in. It tells us the universe began. Because if things are moving apart, we can run things back in the past, and things will be closer and closer and closer, to the point where everything in the universe was on top of everything else. That's the time of the Big Bang. Now, what I was able to do is to go back and use the technology of the day, the brand new telescopes, brand new digital detectors. And I was able to go and look not just in the nearby universe where we see things expanding, but the very distant universe. The universe which light had taken billions upon billions of years to reach us. And when we did that experiment and we saw how fast the universe was moving apart back then, it was moving apart slower in the past and had sped up. Now that was a big surprise, because we all know about gravity. Gravity has everything attract everything else, and that's fundamental to that force.
Well, it turns out it's not. Because in our universe, gravity is not slowing the universe down over time. It's speeding it up. And it's gravity that's speeding it up. It's gravity that's pushing everything apart. But it's not the gravity between you and me and other stars and other galaxies. Rather, it appears to be the gravity of space itself. Space, every cubic meter of space across the entire universe, appears to have, as part of it, energy. And it turns out that Albert Einstein, when he formulated his equations of general relativity back in 1915, realized that if space itself had energy, then that would make gravity push rather than pull. So from my humble beginnings back in Alaska, I was able to use the technology of the day and to build on all of what humanity had done over the previous hundreds upon hundreds of years to realize that the universe was speeding up. And that means that 70% of the universe, as we calculate, is stuff we didn't know existed. It's the energy of space itself. And one of the problems, of course, is that people say, well, what are you going to do next? And the answer is, I don't know, but I'm not going to discover 70% of the universe again, because you can only do that once. But there are so many interesting things to do in science and so many interesting questions that I promise you I have lots to do, and you all have even more to do. So one of the important themes of this is to realize that I'm not a special person, particularly. I'm special in that I had the opportunity to make that discovery, but that discovery was going to be made by someone. And one of the things that you realize when you get to meet all the people I've got to meet who have done many of the amazing things that we think of in the world today is they're all just like me, and we are all just like you. We are humans who have had the opportunity to go out and do something, and we didn't know it was going to be big. We were just doing it because it was interesting. And each of you will have that opportunity in your life. And I can't guarantee that you will discover 70% of the universe, win a Nobel Prize, but it doesn't make any difference, because the real fun part is actually doing the exploration itself. The Nobel Prize is the celebration we all have after the fact. But each of you is capable of doing that, as capable of doing that as I was. And that's something to think about. Now, when we look at the world today, we have, in many sense, it always looks scary. When I was a kid, I was worried about nuclear Armageddon. We had something called duck and cover videos, where when I was in second grade, I would look at this thing about what to do when the nuclear bombs fell, which was to duck and cover. This used to cause me nightmares. With the modern media, we get to hear about everything that's going wrong in the world today on a day-to-day basis. And so it sort of feels like it does at each part of history that we are doomed. But we're not. And we're not because we have the power of science and technology and communication to help us through the hard times. But ultimately, those can only help us if we as humanity are able to use those tools constructively. And that's one of the big challenges that each generation has, is to use the tools of humanity constructively. And that will be your responsibility as much as any generations before you. But the difference is different. It is that 100 years ago, when we didn't use the tools of humanity constructively, we had wars, many people died. Now, I would say the stakes are higher, because the tools of humanity are so much stronger, more powerful than they used to be. And in some sense, that is a blessing, because it means we don't use them to their full force anymore, because we know we cannot. But those same tools are the things that will make life better and better into the future, and can enrich our lives and allow 8, or even 9 billion people to live on planet Earth in harmony over the next hundreds of years. But it will not just happen on its own. It's going to require your generation to go in and make the discoveries and to live peacefully to enact those discoveries to enable us to have that great future. And I'm confident we can do it. But do know that it requires a responsibility. We are part of a very large universe. A universe that random things can occur that may be very difficult for us to thwart. I don't think these are going to happen. They're very unlikely. But there are reasons why, for example, we're scouring the skies looking for asteroids and comets that might plummet down on Earth. But in the very long future, 500 million years from now, the sun is going to heat up. Its nuclear reactor is going to cook the Earth. So we have 500 million years to sort out, as Earthlings, what we're going to do about that. We go to Mars for a little bit. That'll give us another 4 billion years. But eventually the sun's going to die. And so we're going to have to think about really doing the moral equivalent of interstellar. Probably not in the next 50 years like that movie suggests. But at some point, if we want to survive, we need to do that. And the amazing thing is that as humans, we actually have the tools through our intellect to mount those challenges. They're not impossible. They'll be hard. They're not impossible. And so, again, each of us will be part of that. And you need to realize that the reason we have got to where we are today is because each human has been able to input into our collective culture and knowledge. And every good thought around the world is collected now and shared. And it's through that collective work that we are able to make the progress that we are today. And that may not be obvious to you, but it's obvious to me because I see from my vantage point how everything around the world feeds in to the collective good. And you should know that, as I said, you have the opportunity to be part of that. In the very long term, things are grim. One of the things that my discovery says is the universe is speeding up. And the more it speeds up, the more it wants to speed up even further. It's a runaway process. And so, in the very distant future, trillions of years from now, our universe is going to fizzle. It's just going to fade out. And everything will come essentially isolated from everything else in the universe, and we'll look out into a deep, dark void where nothing happens. Now, that may make you lose sleep. It doesn't make me lose sleep because that's 1,000 times longer than the Earth has lived itself. So it's in the very distant future. And you have to realize that humans have only been on Earth for 100,000 years. And if you think about that, in the lifetime of the Earth, 4.54 billion years, if we were to think of the Earth's life as being a 24-hour day, humans have been on it for the last 2 seconds. So humans came on, if it's midnight right now and the day started at the birth of the Earth, humans came on at 11:59 and 58 seconds. So time is enormous, and time will enable us to do almost anything you can imagine, but it's also the enemy because it is ultimately what allows us not to achieve our ambitions. All right, so on that somber note, I think I will stop and open it up for questions. Remember that any question is good. Trying to ask such a hard question I can't answer it gets you no points at all. I like easy questions. Tell everyone your name just so they're proud of the fact that...
Hi, my name is Chandler. Have you ever seen the universe expand?
How do we see the universe expand?
Or have you ever seen it? And what does it look like?
Well, it happens very, very slowly. Okay? So here's how I see the universe expand. I look at a galaxy, okay? And I measure its distance. So for example, imagine that I measure the distance to a galaxy as being 100 million light years. That means light has taken 100 million years to reach us. How have I done that? I've looked at a star, and I've seen how bright that star is. And I've compared that star to how bright it is in our own Milky Way, where I've been able to measure the distance through some other methods. So the further away an object is, the fainter its stars appear. So I'm able to measure the distance to that galaxy by how bright this particular type of star is. The other thing I get to do is I get to measure the galaxy's velocity, or apparent velocity. And I measure that using something akin to what we call the Doppler effect. So we all know the Doppler effect affects sound. As a siren goes by you, it changes pitch. If an object has motion, its light changes its color or its wavelength. So we can measure, it turns out, to incredible accuracy, the velocity of objects. And so, okay, I have a distance, I have a velocity, I know how fast, it turns out these objects are all moving away from us. So I measure its velocity, I measure its distance, and I can say, well, that object's a certain distance away, it has a certain velocity away from me, and I can divide the two, and that tells me how long it took to get from where I'm at to where it's at. When it was where I'm at, that was the time of the Big Bang. So I can see not the actual expansion, but I can see sort of where we're at right now. Okay? An interesting experiment that we're going to be able to do over the next 20 or 30 years is to actually see the universe expanding. We'll be able to see the velocity of that object change over time. But it turns out to be literally centimeters per second per year. Okay? So a centimeter per second is snail pace. But over the next 20 or 30 years, we're going to be able to measure the fact that the universe is expanding at snail pace away from us. Pretty remarkable. Good question.
Parallel universes?
Do I believe in parallel universes? So the answer is, I don't believe in anything. I only believe in what I can observe. Okay? So, and even when I observe something, I'm always a little suspicious that my observations might be flawed. So let's think about what science is. Science, to my mind, is about coming up with a set of ideas, which we would call a theory, and then we test those ideas with observations. Does the theory predict what we see in the universe? And that's fundamentally the basis of what a human thinks is reality. Whether or not it's why a chair works, how the construct of atoms are, how the universe is accelerating. So the problem with parallel universes is no one has come up with a way to test that they exist. So I can go out and I can postulate that there are parallel universes. I can postulate that there are turtles pulling the universe apart, and that's why it's expanding and accelerating. Turtles are getting bigger and faster over time. But I can't test those ideas. So if they're not testable, are they real? That's an interesting philosophical question, because they may well be real, but if we cannot possibly know it, then we have no idea that they are real. And so, to my mind, parallel universes currently are in that form. We can't test them. They are an interesting idea, but until we can test them, they remain a speculation, or more in the realm of what I would say is metaphysics, rather than physics itself.
Hi, I'm Christoph, and if light speed is the fastest movement we can go, and light is the only object that goes at that speed, then how does a black hole suck in the light?
All right, so one of the interesting features of general relativity is it features the idea that nothing can go faster than the speed of light. And it turns out that although nothing can move faster than the speed of light, space can be created faster than the speed of light. So, if you get to a black hole has created what we call a singularity, a place where essentially space goes on forever. Okay? How did it do that? Because when it formed, it was able to stretch space and essentially make light's ability to get into it take forever. Now, in the process, when you look at something, so let's say that you fall into a black hole, and conveniently, you have on your face a clock face. All right? So we're watching time go. And as you fall in, you're going to be redshifted, as we would say. That is, your light will be stretched. Turns out you will be stretched too, because the gravity of your feet will be 1 billion times stronger than the gravity of your head, and we call that spaghettification. That's where you turn into spaghetti. So if you go see the movie Interstellar, it's great to go into a wormhole, but it tends to make you infinitely long, and your body isn't very good at dealing with that. But don't worry about it. It's a good show anyway. But your clock, it turns out, as you get closer and closer to what we call the event horizon, or the edge of the black hole, time is going to go slower and slower and slower, and eventually your clock will stop. But from our point of view, that will happen in infinite time in the future. But if we were watching you fall in, as you would have this horrible look on your face as your feet go to infinity, as your head stays and looks at us, we would see your clock stop as you fall into the black hole. But from your perspective, it'll take an infinite time. From our perspective, it'll take an infinite time for you to get down there, because the amount of space created has essentially been, infinite to this edge.
So does light velocity change?
Nope, it keeps on going at the speed of light. So light's velocity never changes. It's the creation of space that changes. And from light's perspective, there is essentially no time. So if you're not moving at the speed of light, time exists. But if you're moving at the speed of light, it turns out there is no time. You just keep going. But that's why only something that has no mass can go the speed of light. All right? So these are big, deep concepts. Oh, that seems to have scared everyone. Okay.
Hello, I'm James. And considering other options or other career options that are available to you from where you came from, why astrophysics?
Why astrophysics? So my entire childhood, I always knew I wanted to be a scientist. My father was a scientist, a biologist, and while he was doing his PhD, I was a young kid and he had to babysit me most of the time. So I got to see him love his science. And so I always knew I was going to be a scientist. And I became very fond, and still am, of the weather. So I became convinced when I was about 7 that I was going to become a meteorologist. A big word for me when I was 7. And so I would hang out at the forecast office and get the little charts that would come in from the satellite and try to predict the weather. And until I was 17, this is what I was going to do. And when I was 17, I went through and went to the forecast office at Anchorage and said, "Can I volunteer for the summer?" And they said, "Okay." Kind of weird for them. "We don't have to pay you any money. Fine by us. We'll give you a desk." And when I did that, the forecasting office doesn't do science. They do forecasting. The science is done elsewhere. And suddenly my dreams for the previous 10 years of my childhood were shattered. And I had already started applying to universities. I'm like, God, what am I going to do? I don't want to do forecasting. And so I said, well, I don't know what I'm going to do. I do astronomy for free, so maybe I'll do astronomy. And I had no belief that I would ever become an astronomer. But I knew if I did astronomy, I was going to learn physics, I was going to learn math, I was going to learn some engineering skills, I was going to learn computing, and I knew those were all skills that were going to be valuable to me no matter what I did. So my belief was that I would do this degree and then I would get a job in industry doing something using those skills. And in that sense, I was very deeply insightful. That's exactly what most people do. In my case, I did much better at university than I was expecting, and I was able to get into a very good graduate school at Harvard and do my PhD in astrophysics. That is not what most people get to do, but some people do. But it's quite remarkable. Those skill sets that we use in basic research for something like astronomy turn out to be very easy to apply to a whole bunch of things. And so, in my case, that's what I always thought I would do, but I haven't had to do it yet. Maybe someday I'll have to leave astronomy and do something else. But at this point, haven't had to do it. And I think that's a very valuable thing to realize, is that when I give advice to people about choosing a career, you should not do a career, especially when you're 16, 17, 18, trying to decide, based on what other people think you should do. You should do something that is interesting to you, because if you do something that is interesting to you, you will do it well. And doing things well is what ultimately allows you to get a good job. And it may eventually be you have to do something that isn't exactly what you intended or even your first preference. But the skill set of what you learn, well, doing it well means you will learn those skill sets really, really well. And that's what ends up being incredibly valuable into your life. So that would be my best career advice.
My name is Gautam, and I have a question on entropy.
Oh, geez, entropy is always hard.
We often describe entropy as going from order to disorder.
Yep.
But when you make something like crystals,
yep.
You have a solution, and I would call that the disorder state for every single particle in there. But then, if you just take a thread in there, it forms a crystal, and crystals at the atomic level are very, very ordered.
Yes.
So, is that a violation of the second law of thermodynamics, or, I mean, what happens?
So, it turns out that for everyone else on a deep one, I'm going to have to think through this one and see if I can come up with a on-the-spot, I should be able to, I haven't thought about entropy and crystals for a long time. So, the way we describe entropy is essentially how many states there are, okay? So, the more, I guess, the more states that the matter fills, the more entropy it has. Now, entropy, you can temporarily go through and reach states of more entropy, or less entropy, but in the long term, you tend to go to higher entropy states, okay? So crystallization is a cooling process, and ultimately it is a higher entropy state. So if you use what we would describe as statistical mechanics, and you count, because things are more highly bound, you count how many states are in a crystal compared to a random gas, there are more states. And so you have moved to a higher entropy situation. That was a technical question.
First off, would the acceleration of the universe, expansion of the universe ever exceed the speed of light? And if so, how would that affect the perspectives of
10 billion years from now, and I look there, it turns out that I will see all of those galaxies, but their light will be redshifted. So the further away they are, they will have only advanced in the most distant objects a couple million years in their lifetime, despite 10 billion years going through. Eventually, they will be redshifted so much I won't be able to see them anymore. And so, as they come back 100 billion years, it turns out that of those 200,000 galaxies in the moon area, every single one of them will, in 100 billion years, be redshifted so much that their light will essentially be undetectable here at Earth. They will be further away than any object we can see currently with our current telescopes. And that will be true across the entire sky. we will look out and we will see no galaxies. They will all be too far away. But we will also be looking on to our own galaxy, the Milky Way, which will be full of stars, and more stars than it has now. Why? Because we will have merged with nearby galaxies and formed a supergalaxy, the Andromeda spiral, the Triangulum spiral, our own galaxy, a couple other galaxies that have less interesting names, will have merged together to form a supergalaxy. Stars live for about 100 trillion years, the smallest stars. So there will probably still be planets and still be life out there. We assume we're not alone. Or maybe we will have moved to one of these things and we'll still be there. And so we will look out onto this swarm of stars. Our part of the universe is not expanding. It's the space between the galaxies that expand. And the reason our part of the universe is not expanding is because of gravity. The density of space is 30 orders of magnitude less than the density of the Earth. So our part of the universe quit expanding billions upon billions of years ago, 13.5 billion years ago, and the Milky Way formed, the Earth formed. And so we're sort of this little nucleation of stuff. Other galaxies are other nucleations of stuff. And in between us, it's the space that's expanding. So we will see our own stars, but we will see nothing else. Eventually, it turns out that all those stars will die. And so then we'll have a bunch of dead stars. And we think, but we're not sure, eventually the atoms that make up the stars will eventually evaporate. And when they do, those little evaporations will get out into space. And so every atom in the universe will be eventually separated from every other atom in the universe.
So the expansion of the universe is a product of the empty space. So how does that force emanating from empty space?
So it turns out that gravity affects empty space, and the other forces of nature do as well through quantum mechanics. So one idea is that the forces of nature, the three forces of nature that really make quantum mechanics work the way we know, other than gravity, are actually through the Heisenberg uncertainty principle allowing things to come in and out of existence. So it turns out the Heisenberg uncertainty principle, which is one of the foundations of quantum field theory or quantum mechanics, states that pretty much anything can happen given a short enough period of time. So this manifests itself as atoms coming in and out of existence, or particles coming in and out of existence for very short periods of time. So what we believe is that in space, these forces of nature are causing particles to come in and out of existence all the time. Well, those particles have mass, and mass is equivalent to energy by E equals mc squared. So that means that the Heisenberg uncertainty principle allowing things to come in and out of existence will give space energy. The same energy we need to cause the universe to accelerate. The problem is, when we use our theory and calculate how much energy there is, the number we get is 120 orders of magnitude, so that's a 1 with 120 zeros behind it, larger than what we have measured. So it turns out that that is the most catastrophic physical prediction in the history of humanity. That is, it's the most wrong anything has ever been by many, many orders of magnitude. You know, when you get things wrong on your homework and you're off by a factor of 10 and the teacher decides not to give you any partial credit because you were an idiot and you didn't sort of figure out that it was at least kind of wrong. We're off by 120 times, 120 orders of magnitude more than that. So it's a real big mistake. We don't understand it. So we fundamentally do not really understand how the four forces of nature work on empty space. That's one of the ideas behind string theory, is trying to put together how gravity and the other forces of nature come together. We don't really have that yet. So it's one of the big mysteries that needs to be solved. Good luck. It's left a lot of people scratching their heads over the last 20 years, and even Albert Einstein tried to do it and never could do it.
The role of science in our lives. And it seems like one of the biggest challenges we have is that our world is kind of shattered into these separate moral communities. And there's this really entrenched idea that science deals with facts and a description of the cosmos and how it is. But when it comes to how things ought to be, how we ought to live life, that science should remain mute on those questions. And what I'd like to get from you is a sense of your response to that dichotomy of facts and values and the role of science, but more particularly, can science be the vehicle for us to converge on a truly global society? And if so, what needs to change for that to happen, particularly in education?
Okay, so I think at some level, science is a bridge. It is a bridge that brings humanity to work together, work collectively, to work in a language we can all understand, towards goals that we all understand. Science is literally the most international thing that humanity does together. Well, we fight over the idea of what's going on in Ukraine. You know, the American astronauts, you know, jumped into the Russian side of the space station due to some possible ammonia leak, you know, earlier this week. Work very collectively there. And throughout science, we have always worked collectively. But science can work collectively, but ultimately humans work politically. And as much as I would like for us to say science is the moral framework by which all of humanity should work, I think it's part of it. I think it's a way of interpreting and understand the world, but it doesn't give you ethics. It doesn't have a morality to it. It has probability, and essentially something is shown to be correct or not correct, but it doesn't have those human things of what's right and wrong. So humans really need to bring together that morality and ethos, and science can be the way to work together, to work collectively together, but we do have to have something else, in my opinion, to the framework that allows us to use the science to progress. So, for example, how much money should we spend on science? That's not a scientific question. That's a political question. I can argue that these are the things I can do that are good with science. These are the things, of course, science can do bad things as well, but there's a value, a political value that needs to be done there. I can make the decision, let's try to treat malaria. So imagine I want to treat malaria in Australia. We have no malaria in Australia. Why does Australia then put a lot of money into treating malaria? It's an ethical decision. It's not just because we occasionally travel to parts of the world that have malaria. We do it for other reasons. And those are not scientific. Those are part of being human. So the science is the bridge, it's the tool, it's the way we can work together. But we also have to make that decision to work together based on our moral and ethical values. And those moral and ethical values, I sometimes think we don't think enough about as scientists. They're very important, especially, I think, looking to the future. And it's not something an individual can do. Individuals can lead, but it's a collective decision of what we all do that matters. And especially when things get rough. It's easy to work together when things are going well. But it's when things go poorly, that's where you gain the most by working collectively, and where it's the hardest from our own ethical and moral values to work collectively.
Back to something that you said earlier about the expansion of the universe.
Yep.
You were talking about the universe expanding and light not being able to catch up with the creation of space. But if you consider, I don't know, to me logically I was thinking, if you consider the universe to be kind of in a round shape and you said everything's expanding,
and then light would never reach us, but eventually if we were just another particle of other particles expanding faster from one another and distancing further, wouldn't we eventually catch up with the speed of light physically, like us ourselves? Wouldn't we, at some point in the future, in infinite time, wouldn't we just catch up with light? Like, wouldn't, I know light would travel back to us, but if we were, you know, if space was created between us faster and we were still part of that space, wouldn't we eventually reach light?
So it turns out that when you do the geometry of it all, the universe is very well constructed, such that, let's say the universe is what we say bent onto itself. So we call that a finite space. That's a universe which bends around in a fourth dimension and bends onto itself. So if I head out that direction, I'll eventually come back to where I start. That turns out that universe really struggles to accelerate. It essentially won't, you can't have continuous acceleration in a universe shaped like that by the laws of general relativity. If that was our universe, light will literally come back on itself. You'll see copies of, you know, the universe onto itself as light goes around and around it. In a universe that is accelerating, it ends up sort of by definition ending up being infinite in its size. If not initially, eventually. It eventually gets to an infinite size. And in that expansion, there's no way for us to essentially catch up with light. Light heads out and never comes back. So in a universe that is accelerating, one where the universe goes faster than the speed of light, there is no way to effectively see light again. It's only in these finite universes, the ones which are bent onto itself, these universes have a beginning and an end. So, if you think about this, right at the time of the Big Bang, light might have been emitted, and that light will go out and go around the universe, and as the universe comes down to what I like to call the Gnab-Gib, the Big Bang backwards, that light will reach us again. So we essentially catch up to the universe in that case.
Only be created through active observation or passive experiment.
Yes.
To what extent do you agree with this statement?
I'm guessing this is part of the IB program or something. Yes. Knowledge can only be created by active
experiment and passive observation.
Well, okay, so at some level, I would say that knowledge, that is 2/3 of the way there. I've told you what my philosophy of science is. Ideas, testing. Knowledge, reality, is an idea which you test. So imagine I passively observe this audience. So what's one observation I could make of this audience? I look out and I say, we've had 12 questions, and they've all been done by males. So maybe that means the females of this room, for some reason, don't have vocal cords. Okay? So that is an observation I can make. So I have an idea, and then I can test it. And I'm hoping, ladies, that you will refute the idea that you don't have vocal cords. Okay? So that's the process. So you can go through and you can make passive observations to come up with your initial hypothesis. You can do knowledge, and you can go through and test that through an experiment. And my experiment will hopefully be that someone will raise their hand and ask a question. And then I will learn something about that, and then I'll have a new idea. And as long as that idea continues to be seen in nature, then it's okay. Then I say, well, that seems to be a reasonable version of knowledge. Or it may be that I have some other ideas. It might just be that, you know, the women in the room are shy, and I can test that. And we can go through and we can refine our hypothesis again and again and again. And that's how science works, and that's how knowledge works. So I think passive observation, one idea, experiments, another idea, but then there's the construction of the idea, which I think is missing from that statement, which is absolutely at the core of it. So not everyone can write that on the same exam or you'll get into trouble. And you'll probably be wrong.
Hi, so my name is BK. So you said that the universe is expanding, right?
Yep.
So what that sounds to me like is there's an end to the universe, right? So my question is, what lies beyond the space of space?
What lies beyond the space of space? So if you think the universe does have an edge, okay? And that edge is the Big Bang. Because the universe is not just space, it's space and time. And we know that there is a beginning, 13.8 billion years ago. So there's an edge, and that edge is time, it's not space. When we measure the shape of the universe appears to be infinite. It's infinite into the future, and it goes on forever in all directions, forever. So, does that have an edge? And I would say it doesn't. So the universe's edge is in the past. It's not in the future. Now that may be wrong, because there may be more than just the 4 dimensions of space and time. Maybe there's a 5th dimension. Maybe there's 11 dimensions, as some people would say within string theory. But a universe that goes on and on and on does not necessarily have an edge. It turns out we cannot directly measure that the universe is infinite at this point. It's ambiguous. It may be that the universe does bend around into the 4th dimension onto itself. The shape like a giant beach ball, but in 4 dimensions rather than 3. That universe does have an edge. And that edge is the 4th dimension of time, where the universe can never go out any further than that, and essentially is the Big Bang in a reverse in the future. So the universe has an edge in the past and an edge in the future there. All right? But we don't know that the universe is constructed like that. It may well be infinite. In which case, there's a lot more universe out there than we can see. We can only see the part that light has been able to travel over the last 13.8 billion years. But there's probably in that universe, almost certainly, stuff beyond 13.8 billion light years, where light just hasn't been able to reach us. So there's a bunch of unexplored universe, which sadly we cannot explore because there's no way to see it, because light cannot travel fast enough.
Because you have mentioned that scientists does not have ethical responsibilities.
Oh, we have responsibilities, but yes, but keep going.
Scientists should make some judgments. For example, if one finds any discoveries which might have potential threats to the humankind, do you think he or she should abolish the discoveries, or should just publish it anyways?
I guess there's a fine line about the, how the ethics is. It turns out pretty much any piece of knowledge that we have can be used for good or for bad. Every piece of knowledge. Because that's the way knowledge works, is we built nuclear bombs based on not just one piece of knowledge, but 1,000 years of humanity's knowledge. And nuclear bombs, in one sense, are bad, but in the other sense, they may be the thing that would save us from an asteroid crashing into the Earth. So I think it is very difficult on any given fact for a scientist to make the ethical call that they should not publish a fact because they think it could be used for bad. Okay? But I also think it is the responsibility for scientists to make very strong pronouncements when they think things are being used ethically incorrectly. And again, that is a human discussion, and I think it's not just the scientist's call. I think that's everyone's call. So I'll give you an example. We are having the ability now to manipulate the genome, humans and others, in ways never before thought possible. So imagine I have the ability to clone a human. Well, it turns out we have the ability to clone humans now. We haven't done it, as near as I can tell, but we could certainly do it if we want to. And we have decided that ethically that is a poor thing to do, right? So that same technology that allows us to clone humans also allows us to do all these amazing medical treatments. It allows us to genetically modify foods, which is considered very controversial in some things, but it also probably has the ability to raise the productivity of the earth by a factor of 2 or 3 and allow us to actually live with 8 or 9 billion people on the earth and not all starve to death. So it's a very complex decision for an individual to do things. So in my mind, there are certain things which you should not do. I don't think it would be good to recreate smallpox and test it out on, this classroom, this room. That would be a bad thing to do. But I think the individual facts that would allow you to do that are going to emerge one way or another, and I think it's best probably to publish them. But not necessarily to provide recipes to do bad things, if that makes sense, for people who have less knowledge than you. So I think the knowledge is pretty sacred, but you have to make a decision of how you use that knowledge, and that ends up being the ethical part of it all.
So that means that the scientists are not culpable for the precaution from their scientific outcomes?
I think, again, you're culpable if you do something, again, where I think when you drop the atomic bomb, you're culpable. When you have the knowledge that allows you to create an atomic bomb, the pieces of it, I would say you're not. And then actually helping create that atomic bomb is the gray area, where I would say as soon as you start creating something that can be used, and that's its primary purpose, then I think you start having, you are culpable at some level. And, the further in you go, the more culpable you are. And ultimately, it's your peers that judge you. It's not, what is acceptable changes over time. And what is morally, the morals of a situation is completely different now than it was 100 years ago. So you are judged by the peers of your time of the decisions you make.
Hello, my name is Josh over here.
Yeah, great, thank you.
So on a side note, if you don't mind me asking, what made you decide to move to Australia and teach there?
What made me move to Australia? Ultimately, it was getting a job. So my uncle, my mother's brother, emigrated to Australia in 1973. So I visited him for 3 months in 1980 and in 1985. So I was very well familiar with the country. Never really thought I would live there. I went off, did my PhD. I met my wife, who is Australian. She did her PhD in economics, and then we had to get a job. And we applied everywhere in the world and trying to get 2 jobs at the same place. Turned out that we got 2 jobs in Canberra, Australia, and that's why we moved there. 2 good jobs. We could have lived in the US, we could have lived in Europe, but it turns out that that's where we got the jobs, and it was convenient that, I knew Australia very well. My wife, actually being from Australia, knew Australia very well. But it ultimately came down to being a great place for us to, work and to, and to live. It's a great place to do both.
I wanted to ask, if the black hole sucks everything in, right? Where does it go?
Where does it go? That is a deeply philosophical question. So it turns out that it's not going to be easy for me to describe it for you. It turns out that when I dump something into a black hole, it's there. It still has mass, right? So if I add material to a black hole, the black hole weighs a little more. So can I ever get information back out of a black hole? And the answer is no. This is what Stephen Hawking showed that made him very, very famous, is that you can go into a black hole and you're clearly there, but if you ever try to get out of the black hole, then it turns out that you can only come out as radiation, as energy, with no information whatsoever. All right? So what's in a black hole? The answer is, I don't really know. There are speculations that the whole universe can be constructed where we are right now living in what appears to be a black hole from outside. Now, I think in our own universe, we've measured it well enough, we know that that's not really true. But what goes on in a black hole stays in the black hole. It's sort of like Las Vegas. And I really can't tell you anything else more about it.
Hi, my name is Hannah, and I have a more personal question about your motivation for studying astrophysics.
Sure.
So I listened to you talking about the enormity of the universe and the grand scale of it all, like billions and trillions of years. So I really like to understand your motivation for continuing your studies when you know this will only affect us in like billions and trillions. Like for me, when I think about it, I think it's not my problem almost.
Yeah. So, okay, that's a very good thing. I love to solve problems. Science is all about solving problems. And I could have just as easily become a biologist or a chemist because I love solving problems. The fact that I did astronomy was just by accident. It's what I did because I didn't know what else to do. Why do I find it interesting? Because by solving problems, I learn how things work. And so I'm going to give you an example why it ends up being your problem. Because when I go through and I solve problems, I can use those in other ways. And as I said, if you want to do something well, you've got to be excited about it. And I am excited about the universe and what it does. It's abstract, but the things that we use to understand the universe allow us to do cool things here on Earth. So, for example, one of my colleagues in Australia, a guy by the name of John O'Sullivan, was trying to look for Stephen Hawking's black holes and look for that energy that I told you could come out of a black hole, evaporating black holes. He never found them. But it turns out the things that he used to look for those are the things he used to invent wireless internet, Wi-Fi. And that made him about $500 million and made Australia many billions of dollars, and we all use. So the beautiful thing of exploring the universe is you're creatively trying to solve a problem, and in the process you come up with solutions to not just understanding the universe, but to understanding things here on Earth. Digital cameras. We all have digital cameras in our phones. But where'd those come from? Well, it turns out the US military developed the first ones, and they were kind of interesting. But astronomers said, God, these things are great. And so we had bigger and bigger and bigger ones made, cheaper and cheaper, to the point where we all use them every day. So that was something that ended up being useful. The techniques that we use, I take huge data sets, petabytes of data, so thousands of terabytes. And you want to go through and find out what's going on in that data set so that we can unlock the mysteries of the universe. Well, my student who's doing that said, well, that's fine or good, but I think it's time to go get a real job. And so she's working in a startup in Boston, making as much as I do 1 year after a PhD, using the techniques that we use to mine the data of the universe, to mine your credit card data. And that sounds kind of dangerous, but it's so, the idea is not to do bad things, but to help you shop and get what you want more easily, right? So these things all work together, and that's the way science very conveniently helps the world move forward, is by helping us develop things we couldn't think about, right? Wi-Fi, I guess after the fact, it was obvious. Why didn't we just develop Wi-Fi? Well, no one really had the idea of how to do it. What about the World Wide Web? That was developed out of CERN. Well, no one had that idea. They said, well, we need to be able to do this. Let's build something. And they did. And everyone else said, God, that's a good idea. So it helps provide new ideas that are useful. And I've always been willing to take whatever ideas I have and use them in other things for useful stuff. But on the other hand, I kind of enjoy just answering the questions of the universe along the way.
Wow, we got you a real gift here.
Oh, thank you.
I am not an astrophysicist, and I have to admit, and I hope I'm not the only one, that at certain points during your speech today, my head started hurting a little bit as I was trying to understand part of these things. But it is amazing that you have this depth of understanding and knowledge that's been demonstrated and acknowledged by the greater professional community, and yet you can bring this down to a level that we can all relate to. And this is really important. But I think beyond that, and I think for everybody here in the room, and I mean everybody here in the room, it shows you when you have an interest and you have a passion and you pursue that, great things happen. And that's a message for absolutely everybody. And that's one reason why we make these events happen. So yes, you've learned a little bit more about astrophysics, hopefully. I know I did. And you also get to see what happens when you follow your passions and when you pursue something throughout your whole life. So thank you very, very much. And a little token of appreciation, actually quite a heavy token of appreciation, I might add.